Hello, my name is Ben Moldenhauer, and today I'm presenting a method for estimating the amplitude and phase of oscillating signals, which is basically an improvement on the Hilbert transform that I'm calling the short-time Hilbert transform. This is some work I've done while a graduate student at the University of Wisconsin-Madison, where my advisor is Dr. Matt Allen, who is actually at Brigham Young University now, and this work was sponsored by Sandia National Labs and primarily supported by Dr. Dan Rotkin there. First, let's take a look at the Hilbert transform, which is a signal processing technique that can be used to estimate the amplitude and phase of some sampled oscillation. The Hilbert transform itself you can think of as a filter that shifts the phasing of the input signal by 90 degrees. If you take the input and the Hilbert transformed result as the real and imaginary parts of a complex number, you can form a complex exponential in polar form with the desired amplitude and phase quantities. This is shown in the figure in the top right, which has real and imaginary axes set through time. Taking the original input signal as the simple decaying oscillation given by the blue line on the real axis, the Hilbert transform of that is the green line on the imaginary axis. Combining those into a single complex quantity produces the 3D spiral shown in black. Collapsing that onto the complex plane, like with the pink curve, you can represent the spiral as a rotating vector with an amplitude and phase angle that vary with respect to time. Usually, the Hilbert transform is computed numerically through the fast Fourier transform, or FFT. Well, that makes it very computationally efficient and simple to implement. Doing the Hilbert transform this way produces significant errors if the input signal is not stationary, noise-free, and periodic, which are pretty strict requirements. This is shown in the bottom figure, where a constant amplitude sine wave has step changes in its frequency. The raw signal is in blue, the true frequency is green, and, as estimated by the Hilbert transform, are the amplitude in red and frequency in black. About the step change, the Hilbert transform generates ripples or ringing artifacts that propagate out from the abrupt change and contaminate the amplitude and frequency estimations. So to effectively utilize the Hilbert transform in practice, which for those of us working in structural dynamics means getting the derivatives of the amplitude and phase of a measured response to determine the natural frequency and damping ratios of some structure, it usually requires a significant amount of pre- and post-processing in the form of fine-tuning narrow bandpass filters and utilizing some form of noise smoothing to account for these errors. So in this presentation, I'm basically going over a way I found for improving how the Hilbert transform is computed with FFTs by just combining it with the process of the short-time Fourier transform, where I'm calling the combination of those two ideas the short-time Hilbert transform. First, I want to go over in more detail the issues with computing the Hilbert transform through the FFT and why we get ringing artifacts around any step change in the input signal. I think going over this does a lot to justify why utilizing the short-time Fourier transform is a very easy extension that minimizes many of the difficulties that come with trying to use the Hilbert transform. So let's start by looking at a perfect signal for use with the Hilbert transform, one that is stationary, periodic, and noise-free. The time series is on the left and an FFT of it is on the right. We see that for this sort of signal, the FFT produces a symmetric pair of peaks at the positive and negative frequency bins corresponding to the frequency of the signal. Now, say you have the exact imaginary complement to that real signal, which is exactly 90 degrees out of phase. The FFT of that complex valued signal produces a single significant coefficient only in the positive frequency bin. So putting this together, what we want from the Hilbert transform is an imaginary complement to the real valued input, such that we can put them together and form the amplitude and phase. And from what we've just seen in the FFTs, a way that we can get the Hilbert transformed result is to take the FFT of the real signal, set the negative frequency bin coefficients to 0, and then invert the spectrum back to the time domain. This is what you get if you compute the Hilbert transform this way, where our original real-valued oscillation and its Hilbert transformed imaginary complement are shown in the time domain on the left, and their FFT is shown on the right, along with the FFT of the true complex signal we are trying to approximate. You can see that the coefficients in the negative frequency bins are both numerically 0, and that the signals are basically identical down to numerical precision. But now we'll see that if the input signal is not perfectly suited for that Hilbert transform process, we get ringing artifacts. So for example, what if our signal is still stationary and noise-free, but is not periodic? This is shown in the time domain on the left, where the signal does not begin and end continuously. The FFT of the real and complex versions are on the right, where the real signal in blue has two peaks that are symmetric about zero, while the complex signal in yellow has a single peak on the positive side and leakage that extends down into the negative frequency bins. So now, if we compute the Hilbert transform of the real signal by taking the FFT, zeroing out the negative frequency bin coefficients, and inverting back to the time domain, you end up with the orange curve on the left, which shows prominent end effects. Since the signal is not periodic, there's essentially a step change between the start and end, which produces the ringing artifacts that propagate out from that point. We can gather some more useful information by looking at the FFTs on the right of the Hilbert transform signal and the true complex signal that we are attempting to approximate. While the Hilbert transform result has negative frequency bin coefficients that are numerically zero, the true complex signal now has this non-zero leakage extending out from the peak that we are completely missing, which manifests in the time domain as the end effect ringing artifacts in the estimated imaginary signal. So what can we do to mitigate the effect of this missing negative frequency bin leakage? Say we start with the same stationary noise-free but not periodic signal from before, where the exact imaginary complement has all that negative frequency leakage. The thought I had was, if we apply a windowing function to the signal, we can suppress the leakage in the frequency domain. The windowed signal is shown in orange, and the windowing function is in black, where here I used a 4-term Blackman-Harris window. In the frequency domain, we see that the signals show symmetric peaks at the same positive and negative frequencies, but the windowed version has leakage that is about 4 orders of magnitude lower. So now let's compute the Hilbert transform of this windowed signal. Looking at the FFTs on the right side, the blue curve is the result of Hilbert transforming the windowed real signal, while the yellow curve is from applying the windowing function to the truth curve, and it is what we are trying to achieve with the Hilbert transform in this scenario. The first thing to note is that the leakage in the negative frequency bins in the truth signal is now about 4 orders of magnitude lower than it was before windowing. And while the Hilbert transform is still zeroing out the negative frequency bin coefficients, the ideal values are now 4 orders of magnitude closer to 0. We can see how this difference manifests in the time domain by zooming in on the edge of the windowed result. In the regular Hilbert transform, there is no windowing. The ringing artifacts are proportional to the magnitude of the step change at the signal edge. But in the windowed result, while we still get ringing artifacts, they are now proportional to the size of the step change at the ends of the windowed signal, which the window forces about 4 orders of magnitude closer to 0. So now, as you go in from the edge of the windowed signal, the ringing artifacts quickly become subdominant to the actual desired signal, leading to a cleaner result. So seeing that got me thinking, what is an existing process that already incorporates windowing and FFTs? Why, the short-time Fourier transform, of course. So the short-time Fourier transform is a process where you take some initial long signal and break it into many smaller overlapping segments and apply a windowing function to each before computing their FFT. After doing any spectral modifications to the frequency content in the frequency domain, the altered time signal can be reconstructed by inverting each FFT and utilizing the weighted overlap add method to superimpose overlapping time points. This process is commonly used for manipulating audio, like when shifting the pitch of a sound or applying a digital equalization filter bank. But for our purposes here, we can use the same framework to compute the Hilbert transform. The benefits being that separately computing the Hilbert transform of each segment produces localized estimations of the amplitude and phase, limiting ringing artifacts to only affect the segment that contains the abrupt change in the signal. And the end effects in each segment are confined to the low amplitude edges and can be truncated off of the result during the weighted overlap add reconstruction. So what I'm calling the short-time Hilbert transform is done by just injecting the Hilbert transform into this short-time Fourier transform framework during the modify spectral content step, where you simply zero out the negative frequency coefficients and only reconstruct the positive side. And a small extension of that, you can also zero out portions of the positive frequency bins, such that you can partition and reconstruct only frequency content that is relevant to a desired oscillation, meaning that this can be used as a sort of time-varying bandpass filter. And all of that can be automated by combining it with other techniques like synchro squeezing and a ridge detection algorithm. Now let's see a numerical demonstration of the short-time Hilbert transform by analyzing a simple linear free decay signal. Here's the time series of the simulated ring down for a single degree of freedom linear system with a natural frequency of 20 Hz and a damping ratio of 0.25%. The short-time Hilbert transform was done on this signal with a segment size of 0.2 seconds and an overlap of 90%. This is a plot of the amplitude of the ring down, with the true value given in blue, the short-time Hilbert transform result in orange, and the result from the standard Hilbert transform given in yellow. You can see that the regular Hilbert transform result has significant ringing artifacts that propagate throughout the entire response, while the short-time Hilbert transform result also has end effects at the edge. These do not propagate through the signal to the same extent, and as shown in the zoom plot, they are basically gone by the end of the first full segment at 0.2 seconds. From the derivatives of the estimated amplitude and phase, the natural frequency and damping ratio can also be estimated. As this is a linear system, the true values are constant flat lines at 20 Hz and at 0.25%. Due to its significant ringing artifacts, the Hilbert transform results oscillate about the correct values throughout the response and are particularly bad near the edges. Meanwhile, since the ringing artifacts are suppressed in the short-time Hilbert transform results, its natural frequency and damping ratio are smooth and nearly exact throughout the central 90% of the response. And now I'll quickly go over some experimental use cases, which include the impact response of the C-beam benchmark structure and the forced response of a 3D printed beam system to a sine sweep. The C-beam, sometimes called the sandwich beam or S4 beam, is shown on top, where it is two steel beams that are bolted together at the ends. A measured impact response from this system is shown on the bottom with the time series on the left and its FFT on the right, where there are about 6 modes significantly excited. This is a spectrogram of that impact response, which is a way of plotting a short-time Fourier transform result, where the x-axis is time, the y-axis is frequency, and the color denotes the amplitude, where red is high and blue is low. So the red bands progressing through time denote the ring down of each mode. By taking advantage of the fact that we can select a specific frequency range to reconstruct in the time domain, we can set a passband about only the first mode, effectively filtering out the other modal responses. This shows the reconstructed time signal based on that passband. In each plot, the original response is in blue, the short-time Hilbert transform result is in orange, and the residual is in yellow. You can see in the frequency domain that the first mode has basically been perfectly extracted from the response, as there is nothing left of it in the residual. And based on the derivatives of the amplitude and phase, as determined by a central difference derivative with no additional smoothing, these are the quasi-linear natural frequency and damping ratio of the first mode. The second experimental system is a 3D printed curved beam that was excited by a shaker attached to the base. The shaker supplied a sine sweep from 50 to 150 Hz. In the spectrogram of that recorded signal, we can see how the fundamental component of the response sweeps from 50 to 150 Hz, but also that there are significant harmonics to it as well. Say you wanted the amplitude of just the fundamental. By applying a regular bandpass filter to this signal, would capture the fundamental, but would also include the first part of the second harmonic. With the short-time Hilbert transform instead, you can just define a time-varying passband that includes the fundamental and nothing else, effectively creating a region of interest mask that sets everything outside it to 0. This is the reconstructed time signal from that passband about the fundamental harmonic, where it has perfectly extracted it from the signal while leaving the higher harmonics out. In this presentation, I demonstrated that the Hilbert transform produces ringing artifacts due to truncated leakage in the frequency domain. Trying to use the Hilbert transform in practice usually requires user-intensive bandpass filtering and noise smoothing to compensate for the error brought on by these ringing artifacts. I then showed that an improved process for estimating amplitude and phase, called the short-time Hilbert transform, can be formed by simply combining the Hilbert transform with the short-time Fourier transform. The process of segmenting the signal and applying windowing functions in the short-time Fourier transform suppresses issues with frequency domain leakage, effectively mitigating and localizing any ringing artifacts produced when reconstructing the modified time signal. For future work on this, I'm working on a process of fitting an optimized spline curve directly to the amplitude and phase to get a compact and smooth representation of each, with which you can do more post-processing, like identifying quasi-linear natural frequencies and damping ratios, and integrating or differentiating the fit oscillation. Thank you for listening, and I look forward to hearing your questions.